Hi, my name is Mr. Hyder, and I'm a high school math and science teacher at Lodges Unit School on the Azorean island of Terceira. Students will typically ask me,
"Where would I use this?"
To which I say, on the test.
Haha, no, in real life.
To which I reply, I don't know for sure, but I know if you work at McDonald's, you won't. In all honesty, I don't know what the future holds for you. You may or may not ever use these things in your real life outside of my classroom. But I also know that if you don't learn them now, that you won't be able to use them in a real-world situation if it should present itself. Only you can answer the question of, how will I use this in real life? I use the things I teach all the time, and not just because I teach them, but in everyday life. And this is how. Hi, Austin.
Hey, Mike, how's it going?
Good, how are you? What are you up to?
Throwing some tomahawks, getting
Really?
my practice on.
That's pretty cool. You throw much?
Every once in a blue moon, not too often. And yourself?
Yeah, I dabble.
Sweet. How long you been throwing tomahawks for?
A couple months.
Cool. Show me what you got.
Okay, let's make a bet.
What do you want to bet?
I bet you I can hit this plate first time.
Alright. Sounds good.
Well, Austin, looks like I hit the plate. Hey up.
Well, Mike, I thought the agreement was that the whole head of the tomahawk had to hit the plate.
I don't remember saying that. I remember saying that I'd hit it with my first shot.
I guess I better specify with my bets next time.
You better pay up, too.
I'm a little broke, but how do you do that?
Mathematics.
Teach me your ways, good sir. How do you do stuff like that?
You got it. What's the probability of you getting a heart?
Well, there's, what is it, 13 cards a suit, 4 suits, so 1 in 4.
Yeah. What if you wanted to get an ace?
An ace? Well, there's 4 aces in the deck, 13 cards per suit, so 1 in 13.
Yep. What if we make this into a number line, where you have numbers 1 through 10, and you want to pin the tail on the donkey on number 5? How many options satisfy number 5? Or how many 5s are there? And how many other numbers are there? So then what's the probability?
1 in 10.
Great. Welcome to my classroom.
I'm in a classroom. Haven't been in one of these for a long time. New clothes, sweet stash.
Austin, take your hat off.
Whoa! How'd you do that one?
Austin, get your book out. Austin, can you please read the concept bite of probability and area on page 669?
My book. How'd you do that?
It's mathematics. Please read for us.
Man, it's open up to chapter and verse. But do I really have to read it?
Do I need to snap my fingers again?
Alright, I'll go ahead. Key concept. Probability and area. Point S in region R is chosen at random. The probability that S is in region N is the ratio of the area of region N to the area of region R. So, Mike.
Austin, in the classroom, you refer to me as Mr. Hyder.
Oh, so, Mr. Hyder.
Yes.
Tell me all about this. I'm not quite getting the book.
Okay, so let's look at the image here. So I have my area R and my area N. And in the book, they said that there's an S, which is going to be a point. Chosen at random. So that's going to relate to the equation of the area of N is over the area of R. So let's say this N is very small. the area of n is much smaller. So the probability of me with my S choosing at random hitting the box n is much smaller. What if I make my n really big? It covers nearly all of my R. Well, that means my probability increases. Now, one thing that needs to be certain though is that my S point will always hit at least R.
So, I get it, but now can we go back to your place?
Let's do a sample problem first. All right, Austin, I have a rectangle with 15 by 10 meter measurements and a square that's 6 by 6 meters. We're calling that area A. And a circle with 3 meter radius, we're calling that B. I want for you to figure out for me which area, either A or B, has a higher probability of me hitting if I throw, let's say, a ball at random at the board. If you're watching this online, pause the video and solve.
Okay, so to solve for the area of the large rectangle, multiply it 10 meters by 15 meters and you get 150 meters squared. And then for the smaller square, it's 6 times 6, which is 36 meters squared. And then 36 over 150 comes out to about 24%. And then for the circle, it's a pi r squared. So the radius is 3 meters, so that would be 9 meters squared times pi would be about 28.2527 over 150 will come out to about 19%. So the higher probability would be with the rectangle.
Well, this is all great in practice, but do you want to start throwing some things? All right, Austin, give it your best shot. How'd you do, Austin?
I did alright. I got I think 1 in the A. So yeah, that's about 25%.
Great. So the theory makes sense?
I'd say so.
Let's get out of here. All right, Austin, here we are. Let's find the area of the wood block and the paper plate.
Alright, well I know a rectangle is pretty easy. It's just width times height. So the width is going to be, we'll call it 22.5 inches.
Good.
And then tall is, we'll call it 21 to make it easy.
Okay.
So, a circle. A circle is, what is it, pi r squared?
That is correct.
So r would be radius. But how do I know what the radius is if I don't know where the center of the triangle is?
Well, we don't need to know where the center of the circle is. We just have to find the diameter and divide by 2. So 2r equals d.
This is 9 inches. So 9 divided by 2 would be a radius of 4.5.
Good. We have all our calculations. Let's do some number crunching.
So the rectangle came out to 22.5 inches by 21 inches, which comes out to a relatively easy mental calculation of 472.5. So then our circle had a radius of 4.5 inches. So we'll square that, and we'll get 20.25 inches. Now, to get the area, we need to multiply that by pi. So 22.25 multiplied by pi is going to come out to 63.6 inches squared. Alright, so from the key concept that Mike showed me earlier, N is the plate and R is the wood block. So the area that we got from the plate was 63.6 inches squared. And the area from the rectangle, or from the block, was 472.5 squared. But if I do the math, it's going to come out to something like 0.13 because the squares cancel each other out. So this is like 13%. Alright, so Mike, the math shows me that this tomahawk should have only hit about 13% of the time. How did you hit the bullseye on the first try?
13% doesn't dictate whether it's the first, second, third, or fourth try. It's just that roughly 1 in every 10 will be a bullseye.
Can we give it a go and see if the math is right?
Yeah, why don't we have you throw it 10 times and see if you can hit it once. And that would be close to 13%.
Sounds good. Let's go. I like seeing the representation on how the math worked. Do you have anything else we can try?
Yeah, I think I got something else we can do.
Alright, let's see.
Well, let's figure out the probability of me hitting the yellow bullseye.
Alright, well first, let's get the dimensions of the center bullseye. The center's identified for us. So the radius is about 2 1/4 inches. And then let's get the so the target is going to be 24.5 inches by looks like 24.5 inches. Perfect square.
Good. Let's do some number crunching.
So the radius of the circle was 2 1/4 inches. So that times itself comes out to 5.1 inches. And if we multiply this times pi, we get 16 inches squared. Then, for the square of the target, we had 24 inches by 24 inches. That came out to 600.25 inches squared. So, to figure out the probability of hitting the target, N as the bullseye and R as the target, we're going to divide 16 inches squared by 600.25 inches squared. That's going to come out to 0.026 or 2.6%.
Well, Austin, it's 2.6% chance that I'm going to hit the bullseye. I bet you, double or nothing from our tomahawk bet, that I can hit the bullseye 3 times in a row.
3 times in a row? Well, the probability of hitting once is 2.6%. So my odds seem to be pretty good. I'll take your bet.
Well, Austin, I count 1, 2, 3 bullseyes. Pay me my money.
Now come on, Mike. I feel like I've been worked over and cheated a little bit. I mean, you got the plate on the first time with the tomahawk, 3 bullseyes with the bow and arrow. What's your magic? What are you doing?
So you're saying that either the math is wrong or I've got tricks up my sleeve.
I think so.
Well, there's a difference between theory and applied math. What you don't know is that I've been shooting bow and arrow since I was 5 or 10. And I also dabble far more than the average geometry teacher does with tomahawk throwing. So in all likelihood, I could hit that probably 9 times out of 10. And I could hit this 100 times out of 100.
All right. I'm seeing here that 1, 2, 3 times he shot, he was within 1 inch of center. So let's make a 1 inch circle our new R, and this euro cent, our new N. I bet he won't be able to hit that every time.
All right, Austin, I'm gonna take your bet. Before I do, I want to figure out how many arrows I should fairly get. So, I'm gonna do some math. Gonna figure out the area of the euro cent and the area of my new R. So the euro cent's gonna be N, and the area of the 1 inch circle is gonna be R. Now, I don't have to actually figure out everything with pi in it, because these pi's are gonna cancel out. 1 times 1 is gonna equal 1, and any number divided by 1 is itself. So the probability is gonna be 0.25, or 25%. So, I will make this bet with you, but I get 4 arrows. So Austin, what'd you learn today?
Well, I learned, first off, teachers have an alright time outside of the classroom. I also learned that this probability and area stuff is pretty applicable, you know, maybe playing darts or what side or what part of the goal you might hit in a goal if you're playing soccer, so it's pretty interesting.
Great. Did you have fun today?
I'd say so.
Okay. Now never sit at my desk again.